Okay, so so Felipe talked a little bit about the Hirschman's vibration theorem. For so he gave a proof, but there is a I have to say that there is a proof using symplectic geometry. I prefer that book, but anyway. The moral of the story of a Hirschman's vibration theorem is that from the infinity point of view, a lot of varieties that we have, they are the same. For example, all smooth hypersurfaces. So, but let's go to the 14th lecture. Okay, so I have to do something else before again. I have to open another. Once again. I didn't prepare my. I have to see my own book. Okay, today, the idea is that I want to define polarization and so on, and at the end, the idea is that to reach the definition of a Hodge cycle. So I'm going to section, well, let's say, before going to section 5.6, starting from this section, I am going to, I will say a few words, let's say from my book with my text with the Roberto. Okay, first maybe some remark. I have a kind of remark. This is a very easy remark. Fi. We define the Hodge filtration of X smooth projective variety over K, and if we make the Fi cup product with Fj, remember that I told you that there is a closed formula for the cup product, in this case Fj Hm2 the Rham X. This is always algebraic the Rham cohomology. So this observation, it is good to make before going to the general context. And so if you make the cup product in the E space of the Hodge filtration of Hm1 and G space of there is something extra here. Fj of mm2, this is Fa plus, it goes to the Fi plus J piece. This is a kind of immediate with the from the definition of the cup product and the Hodge filtration. So remember that the elements here, let's say omega 2 elements here. Actually, let's not with indices. Indices I need it. So omega was something like omega I in the double complex. Remember that there was 0, 0. Then there was omega I plus 1, and then omega m1. And the other one in the double complex was 0, 0, 0, omega alpha j plus 1, alpha m2. And if you look at the formula of the cup product, at the end it is made by making the wedge product. It is a sum where you make the wedge product of these guys with these guys. I'm not going to write down the explicit formula, but at the end then you arrange it in alpha to alpha omega cup alpha. At the end, the first and remember that this upper index refers to differential, the degree of differential form. So what I say, what turns out from the formula of cup product, that here you will get whatever wedge product that you make here, it will be at the end below this I plus j plus 1 blah 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 comma I plus j, comma m1 plus m2, because they're the formula of this gamma i's are just sum over sum with sign of these guys wedge these guys, and these guys wedge these guys. Always they will contribute to something here, and this is exactly the element in fi plus j. So this formula is kind of immediate from the definition of the hypercohomology, and the definition, and not the definition, the formula of the cup product. Okay, so this is one observation. So maybe let's go to the polarization. This is section 5.7, and again let's that takes the pain in. Let's take the coordinate system x0, x1, xn, and let's well, again, you might ask why I define this element, but the proposition after this will make it clear why we are doing in this way. Okay, so the polarization, let me first write and then explain. Okay, so here I will take, for the Pn, I will take the classical covering. Let's say u ui I equal to 0, 1 until n, and within a ui is xi not equal to 0. So I want to define an element in the okay, maybe let's go to the next page. I think this way is better. I want to define a polarization which is in H2 the Rham of Pn, and so this at the end of the day, what it my this is algebraic de Rham cohomology, and again in the double complex, so it is it must contain theta 0, theta 1, theta 2, and let's say for me theta the element that I'm going to define has theta 0 and theta 2 equal to 1, so I have to define theta this theta 1, and theta 1 ig. So remember that this it will be in the so since it is in H2, and for theta 1 I have to define what is theta 1 ig in a differential one form in ui intersected with the uj. And maybe let's just define it simply, and then let's go why we did it like this. Then it will be simply dxj xi divided by xj xi. So xj xi is a function. Now it is a regular function in ui. And okay, again, it might be strange why we define this one. Anyway, let's for the moment just consider as a definition. First of all, this will give really an element in the algebraic de Rham cohomology. We have to check it, and the checking is not so hard. We have to check that, remember that D is delta plus minus 1 J D in the double complex, and G is the lower index of the check cohomology. So we have to check that D of this one is 0, and of course this is the case because when there is 0 here, 0 here. So if we have, this means that if we take of D, this one is going to 0, and delta of this one is also 0. And the D of this one is 0 because this is actually D log xj xi. If you do further D, it will be 0, and also its delta, it is 0 because this guy. Because this guy is, you can write it at dxj xj minus dxi xi. Remember that these are not differential form in ui intersected with uj, because these are the homogeneous coordinate. But because of this aspect, this feature of theta, we see that if you take the delta of this guy also 0. Anyway, we get an element in the de Rham cohomology, and okay, so maybe the actually this definition comes from this proposition, the desire to translate the classical generator of H2 Pn to algebraic de Rham cohomology has produced this element. Anyway, theta in. So let's say H2 de Rham. Let's go to the complex. The infinity context is given by. Maybe I write. I will write it the same. I will the same notation. D bar D. Again, I will just mention it. I think I will not. Xi to the 2 I equal to 0 until n. Anyway, and this theta integration over P1 is equal to Pi. P1 inside Pn, any line. Okay, so what I am writing, first of all, remember that our algebraic de Rham cohomology was isomorphic to the classical de Rham cohomology. So we will mix this together. So if I consider theta inside the classical de Rham cohomology, then my theta is given by this formula. I will again, I will not produce. In the book I have put theta check, but I think let's keep sometime I will not produce different notation for infinite de Rham cohomology and algebraic one. Okay, then, well, I think the ingredients of this one, maybe I have to a little bit explain. As you did, so there is, let's say, this holomorphic derivation and anti-holomorphic derivation. Maybe I have to say about this one. D f z1 z2 zn. This is a kind of C infinity function. Then this is just some df dzi dzi bar, and the usual, this is this differential form, and d bar f z1 zn. This is C infinity function in any domain in Cn. This will be just fi zi bar dzi bar. And And it turns out, and maybe one remark also must be made, is that this guy is not a function in Pn, but it is in Cn plus 1. Actually, one has to write here, instead of this guy, one has to write down it in this way. One has to put x0 equal to 1 and go to the affine chart and write this xn to the n. So if you take this one in the affine chart, then there you will get, you can make dd and d bar, and you will take differential form. And the idea of the differential form will even so that it is defined in the affine chart, it comes from a global differential form. And let me see. Actually, here I have made. I am talking still about Pn. So let's say Pn. Let's say I am considering Pn as C-infinity manifold. And again, I have a differential 2 form. I can integrate over any 2 cycle. P1s inside Pn gives me 2 cycles, and this integration is 2 pi I. Okay, let me see. And the reason why we write in this way, because the holomorphic, if you have here, let me say in this way. If you factor out this x0 outside, then you write it here, and then let me. What I want to say, if you define this one as fx1 fxn, then at the end x0 to the 2 plus x1 to the 2 xn to the 2 is x0 to the 2 f x1 x0 fxn x0, and under dd bar this is cancelled, and that's why we write in this ambiguous format. Anyway, let me see. Okay, the proof actually is not. It's not very hard, and the moral of the story. Well, maybe I will skip the proof. The moral of the story is that. Let me write in on the. Let's say under H2 the Rham Tn. This canonical isomorphism that we had, theta is tet 1 2 pi I. Theta is mapped to let me say that to U to the generator, to the generator of this guy. And remember that this is Z. By topological from our main theorem in topology, we can easily see that this is isomorphic to Z, and then we have this assertion. Anyway, let me see if I want to. Well, really the proof is the proof is not really difficult. I want just to proof after maybe after making the things explicit at the end, the proof reduces to this integral formula r2 dx y dy 1 plus x2 plus y2 to the 2 is number pi. Okay. Let me. Okay, so and at the end of the day, H is star the Ram, the star the Ram, let's say Pn is the ring is generated by theta. So this is the point that we have this H2 the Ram Pn. We make it let's say, so we have to make theta I, theta cop theta cop theta I times, and then theta I will be an H2I of a Pn, and this the if we consider H star together with cup as a ring, then we have this generator theta. Let me say what I want to tell more, and maybe the explicit formula of something that maybe we need it from the explicit formula of the cup product. We have for example theta n. Theta n, it will be the H2n Pn, and in theta n it will consist of just let's if I write here theta 0, if I write it in my way that I was writing, maybe I write omega 0, omega 1, blah, 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 omega 2n. There will be just omega n non-trivial. Omega n, blah, 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 omega n to n. Everything is 0. From the formula, it will except this one. And for this reason, sometimes I will, so that this middle, just the middle piece will be non-zero. And let's say theta n. So in this middle piece corresponds to the intersection of n plus 1, 0, 1, 2, until n. It will be given by this formula. Then xi I equal to 0 until n minus 1 to the I xi dxi hat x0 x1 until xn, and this dxi hat is dx0 wedge dx1 with dxi dxn. Anyway, what I'm saying that if we have this the cup product, we can compute whole theta n, and you see that well, this omega, I use this notation to say that there is just this middle piece, and this middle piece only is defined in n+1 open set, and I have just one the intersection of n+1 open set, and I have just one the intersection of u0, u1, u2, un, and in this intersection theta, this middle piece is given by this. Anyway, it's a kind of let's say explicitly writing the polarization. This element we will need it. Okay, maybe let me just share it, talk a little bit on the screen. Okay, so as I said, the proof is just the translation, how we translate the algebraic de Rham cohomology to C-infinite de Rham cohomology. And the one good point of the proof, that in the proof we don't use partition of unity. We can construct our C-infinity function by this kind of norm function. So the idea is that I can write down this minus theta ij as a difference of two differential forms, and this differential form I constructed using this norm function, and then I will follow the recipe of the isomorphism between classical de Rham cohomology and algebraic one. At the end, in the C-infinity de Rham cohomology, my theta must be given by this d theta i's, and it turns out these are just the dd bar of log pi. So this is a kind of good exercise to understand this isomorphism between C-infinity and algebraic de Rham cohomology. Okay, so let me and again the integration formula, as I said, it follows from this. So at the end we have to check this equality, and we can explicitly compute what is theta m in the check homological interpretation of theta m. And let me go, this one I already told. Okay, so let's go to the top cohomology. We need also to handle this top cohomology. Okay. So again, our X is a smooth projective variety. So dimension X is n, and by definition, of hyper hyper cohomology, then Hm de Rham X algebraic one is 0 for m bigger than 2n, and this is because we don't have any. Let me say in this way why we have this we have this. For this, we take a covering of X such that the intersection of any n plus 2 open set, always affine set, open set is empty, and okay, I already mentioned that we have such a covering. So let's say let's go to this when m bigger than 2n, and when we look for this double complex at the end, remember that there was this Sij, S being the sheaf of differential forms, let's say I forms, X, and well, when and then I plus G is equal to M, and when I plus G is equal to M, it is bigger than 2n, then this implies that either A bigger than n or G bigger than n. Let me see. If I equal to n, if I have a if I is less than or equal to n and G equal less than equal to n, then I plus G will be less than or equal to 2n, which is not my case. So one of these will be happen. But when we don't have, in this case, we don't have differential I form. Remember that our differential form is algebraic. In this case, we don't have, let's say, non-empty intersection of UIs, because this will correspond to, remember that this will correspond to in n it is correspond to n plus 1 open set. So in J it will correspond to intersection of n plus 2 open set, and there we don't have any. Anyway, by the definition of our the Rham cohomology, our 2n we don't have any cohomology. So the first this 2n will be called the top cohomology of X. It is this H10 the Rham X, and something that we will make it. So we have this H2n Pn. It is generated by theta n. We have the notion of restriction H2n X, and this is the restriction map. And yeah, then by restriction map I will denote also this one. I will not introduce new notation. So this theta n will be just a restriction of the other theta n on X. So for simplicity, I will use theta n as element in H2 and X. So I have elements in H2 and X. Okay, so maybe so let's say talk about a proposition 5.4. H2nx H2n the Rham X is of maybe in this case I write a little bit complex. So remember that now X let's consider as our field is a K vector space of dimension 1 generated by this theta n. And the thing, well, for this is let's say k characteristic k 0, but and for k equal to c, maybe I write it differently as in the book. Actually, this the integration of this theta n over x, let's write the x analytic. When I write analytic is degree x 2 pi I to the n. So anyway, this proposition also tells me that I have a control over the top cohomology. I know that the top cohomology of the smooth projective variety is generated by the theta n, and I know its integration over the whole variety. There will be up here degree x and this 2 pi I n, and okay, and actually let me say. So the point, again, I'm skipping many facts from topology proof. The proof is basically if you take this 2 pi I to the n, 2 pi I theta h2 if you consider this one as elements in Pn C infinity, this is the generator. And it is well known that if integrate the generator of H2 over a projective variety, the integration is just the degree of x. And well, I think depending on the need, we can return back, go into the details of all these statements. But my idea is that in order to reach as soon as possible to some computational part of Hodge theory, for the sake of not focusing too much on details of proofs. Anyway, this is so this is the statement about the about the top cohomology. So then we reach to the very nice to some very important concept in our de Rham cohomology. So the concept of trace map. So H2n de Rham x, this is isomorphic. Maybe I write explicitly our arbitrary field k of character 0. This is isomorphic to k, and let's just do the trace of any element here. I have to just compare with its generator. So this means that if I have omega here, I compare it with this theta n. This is a kind of symbolical way to write. Anyway, this is one-dimensional, so I can compare it with theta n, and the comparison gives me a constant, and then there is degree x. Okay, so we will need to handle this this trace map, and in for x.
Hossein,
Fala.
why do you use this factor degree? Like,
okay,
why do you need this?
Okay, but first of all, let me say that this is here. So the if I call this one u, This is a kind of a classical fact that U, which is the generator of this guy, integrated over projective variety, is the degree of X. Okay, so the degree of X pops up here. And let me see. In any case, we have a freedom to, let me remember why I inserted degree X here. The point, the main reason why I inserted degree X here, because I want that trace of theta n to be 1. Because if I put omega equal theta n divided by theta n is 1. Let's just, no, just a moment. No. It's called. Oh, no, actually. Later, I need this fact. This is the reason. So this I will call it the volume form of X. Anyway, I need to fix a generator of H2N theorem X. And it turns out that for later uses, theta n divided by degree X is I have used this as the generator, and I want that this be the volume form. Well, this is kind of just a name, but at the end, the trace of this my volume form must be 1, and that's why I have inserted an X. But anyway, the answer to your question will be clear later when we start using this guy. And let me if I remember well. Yeah, for the moment, there is no reason why we insert this degree X. One can put any number here. Actually, I could. Maybe later we will return back to this question and to analyze where we have used. Anyway, so this is the trace map, and actually the reason why this is called trace map in the topology book I have not seen calling this trace map, but within algebraic geometry it is used as it is called trace map, and I think it comes from an article of Tate, but one has to go and look for it. Okay, then let's go further. Well, the bilinear maps. I will need these bilinear maps. HM theorem X H2N M X going to the field K. What is this? This will be just if you take alpha, if you take beta here, you make what is this alpha beta. First, you can make alpha cup beta. You will go to the top cohomology. Top cohomology is dimension 1, and then you just take this trace map. And okay, another. So this map is non-degenerate, and well, because the same map in the topological context is non-degenerate. And let me remember Hn x analytic z m h2n minus m x analytic z. Then you make cup product. You go to h2n x and z, and you take a generator of this one and you go to z. Anyway, the point is that you see something that you might observe, that I am using the topological statements in order to prove my purely algebraic statement. We constructed this one in a purely algebraic context, and this is everything is algebraic. And at the end, so far, I don't have any proof purely algebraic, just using algebraic theorem cohomology. And this is the case in most of the Hodge theory, that sometimes we have many nice algebraic statements, but the proofs go through topological and transcendental methods. Okay, then we have this another bilinear map. Maybe it is useful to have in mind. And actually, maybe I introduced Hodge-Lefschetz theorem. Before going to HM de Rham X algebraic H. Let me write in this way. Maybe the way I write in the way that I will need it. De Rham. If I take HM and H2 and M, there is a map like this: omega H theta n minus M. So remember that this is M, and this is 2n minus M differential form. At the end, this omega cup theta n lands here. Hodge-Lefschetz theorem says that this is an isomorphism. Again, maybe I write it explicitly here. Maybe not I. There is no algebraic proof of this using only algebraic de Rham cohomology. In the sense that this is we constructed in algebraic context, this constructed algebraic context, everything is here constructed algebraic context, but the proof, unfortunately, the first proof, going to HM de Rham X analytic, let's say the SC infinity manifold, and then it passes through harmonic forms, etc. So the proof really goes beyond the spirit of algebraic geometry, and the other proofs, due to Delin, goes through goes through étale, cohomology, etc. And at the end of the day, in order to prove this statement that we in algebraic theorem cohomology, we have to go through other cohomology theories, and which is kind of strange, because because the statement itself it's purely algebraic. Anyway, at some point maybe we'll begin. We will return back to this hard Lefschetz theorem. But what I wanted to say, this bilinear map that I introduced there, it will imply that this another bilinear map is non-degenerate. H, let's say this H M, the Rham, X, H M, the Rham X to the field K. So this is alpha, beta, the pairing alpha, beta. It is just take alpha, cup, beta, but you don't reach the top cohomology. In order to reach the top cohomology, you have to make it cup to the theta n minus m. This will now reach the top cohomology, and then you take the trace of this. And this is also is non-degenerate because of this hard Lefschetz theorem. This guy is isomorphic to so this map that we are is already here. This is the same as this one. It is just a reformulation of the previous one.
And Hossein, is this still like, it seems to be related to some kind of Poincare duality, right?
Yeah, exactly. What I'm saying that actually I would try to prove the Poincare duality. Well, if we say that this consequence of the Poincare duality, that is non-degenerate, is equivalent to a Poincare duality, then I can state this one in purely algebraic theorem cohomology context. So this means that I have the wish to prove this one purely in algebraic context. But they remember that the Poincare duality is something finer, because these guys, they might have torsions. When you go to algebraic theorem cohomology, the torsions disappear. So in any case, even if we prove this non-degenerate stuff, it will not imply the Poincare duality in the topological context, because these guys as at most it will imply the Poincare duality with coefficients with rational coefficients. For let's say H cohomologies of Xn with rational coefficients. But you are right. And anyway, this non-degenerateness comes from also the Poincare duality. Okay, so let's let me see. I think I am a very bad. Maybe just mention also this one. Okay, maybe this again this the relation of the Hodge filtration on this this bilinear map HM the Rham X. So this, if you take the Fi part, let me write down this Fj part. I will state just for one of the linear. So this is equal to, so the pairing of Fi and Fi choose P is 0 for all I plus j bigger than n. And well, this is a kind of a direct consequences of our definitions. Remember that remember that the definition of this guy, this was what? If I take alpha omega here, alpha here, this was the trace of alpha cup of omega cup alpha. Remember that at the beginning of the course, I told that when you make Fi Hm cup Fj H2n minus m, this is going to be inside Fi plus j h of h, I don't write the Rham, x, and so on, to n. And and yeah, and actually it's something that we have to let's remember. This one I remember again the double complex. So our double complex is full of non-trivial elements in level 2n, level n, and level 0. So here level m, level 2n minus m. But the point is that non-trivial things are just here, are just in this box. The moral of the story is that, similar to the argument that I told you in the beginning, elements omega, let's say, element, let's say, have only, let's say, if I write it omega 0 plus omega 1, blah, 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 omega 2, omega n, blah, 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 omega 2n. So there is just this piece here, which is non-trivial. And this one, this might be non-zero. The rest are 0, 0, 0. Because over here, everything is 0, 0, 0, 0, 0. And just in this corner, we have now something non-zero. Anyway, and let me go to the proof of, okay. So Fi plus G2n. So remember that making Fi plus, what was the making Fi plus G? Fi plus G was corresponding to taking filtration, let's say, from the A plus G. So everything on top of, maybe I have another color. Okay, if this is 0, 0, 0, 0. So, if I am talking about Fi plus G, this means that from the elements downstairs can be arbitrary, and upstairs, by my definition, they are 0. Since this anti-diagonal has just non-zero elements here, this means that if my I plus G is here, down here, then my filtration is automatically 0, because everything downstairs is 0. At the end, I plus G, that's why I plus G, when it's bigger than n, note that this is the n place. Here is state Sn, n, S my sheaf, and here I have Sn plus 1, n minus 1, and so it goes on. And these places all are 0, and this means that when I plus G is bigger than n, then I plus G is bigger than n implies that Fi plus G, H2n is equal to 0. And since we have this one, then it will follow that this guy equal to 0, because we make coproduct of this one, it will be in Fi plus G, and Fi plus G is automatically 0. So it is nice to carry in mind also this equality. Okay, so maybe let's. So next time, what I'm going to do, I'm going to talk about the cohomology class of algebraic cycles, and then I will define the notion of Hodge cycle. So once again, this is not a classical way of presenting Hodge theory. I am trying to avoid these harmonic forms, Hodge decomposition, and so on. I'm trying to present Hodge theory just as a package of topological and algebraic tools. And yeah.